Welcome to this final exam review for computer organization. Let's get started here. The first question over here is as process design technology allows engineers to put more transistors on a chip, microprocessor companies are increasing the number of cores on each chip. What other feasible choices could they have made instead? So basically what this question is saying is with every passing year as our process design technology evolves, the size of the transistors is shrinking. So essentially in the same given chip area, let's say this is our chip area, we are able to fit more and more transistors with every passing year. Increased number of transistors basically translates to increased functionality that can be implemented on the same chip area. So the question is, how can we, what are several different ways in which this flexibility can be used? So the way it is currently being used, as the question says, is let's say last year, so I'm just this is just a hypothetical example. Let's say last year the transistor technology was at a place where in this given chip area we could implement only two cores. We could only fit in so many transistors that were sufficient for two cores. But let's say this year, with the evolution of this process design technology, now we are able to fit two times more number of transistors in the same chip area. So one possible way of using this evolution is that in the same chip area, instead of two, we now implement four CPUs or four cores. Now this is obviously one way of increasing the functionality. What else could we have done? So well, the other obvious thing we could have done is, let's say we kept the number of cores constant. So let's say we still implemented two cores, but then uh, we could have increased the size of the cache on chip, right? So maybe we could have increased the size of L1 L2 caches, and maybe also the size of, let's say this is the shared L3 cache, right? So this is another way of increasing or improving the functionality on the chip. So the question is why this is not done, right? Why did the designers choose to go with increasing the number of cores and not increasing the size of the cache? So the main reason it is not as beneficial to increase the size of the caches is doubling the size of cache will certainly help improve the hit rate, and obviously, as you would know, increased hit rate means that we can satisfy more of our data and instruction requests from the faster caches, and we have to go to the slower main memory less frequently. However, the problem is, if you think about this, let's say right now your L1 cache is let's say 64 kilobyte in size, and let's assume that you double it, you make it 128 kilobyte. This L1 cache, which is 64 kilobyte, typically this would already have a hit rate of more than 90%. Okay, and if you double it, this hit rate will go up from 90% to, let's say, 93%, right? So just by doubling the size of the cache, the hit rate does not double. There is not so much room. You will go from 90 to 92, 93 or 95%, right? So the gains that you're getting are marginal. As opposed to this, if you deploy these additional cores on the same chip, then on each additional core you are able to execute additional processes, additional threads simultaneously in parallel, right? So you have increased amount of parallelism, and you can run more number of processes and threads, which will provide much greater computation improvement as opposed to just enhancing the size of the cache. So that's the main reason that designers have chosen to go with implementing more cores as opposed to increasing the size of the caches, for example. The answer is also summarized over here. So the next question over here is, why do interrupt service routines have priorities associated with them, whereas normal procedures do not have priorities? So let's think about how processes execute functions, right? So let's say in your code you have a function fun, and let's say this function calls fun1, and then it calls fun2, let's say, right? So the way this works is when your code reaches this point of fun1 call, it will jump to function fun1, execute it completely. Whenever fun1 completes, it will return, and then it will start executing this next function called fun2. Whenever fun2 finishes, it will return and start executing the next line of code in this function in this function fun, right? So the thing is, with normal procedures, the the order in which functions should be called is completely dictated and determined by the program itself. As opposed to this, with interrupts, let's say the CPU is routed, let's say CPU right now is serving some interrupt I, right? And the CPU is not yet done, and in the meantime, in between, let's say another interrupt J arrives. Now the question is, CPU doesn't know whether it should keep executing, keep serving interrupt I, or should interrupt I be suspended and interrupt J be served instead. So some way is needed for the CPU to decide which of these two interrupts is more important in some sense or more urgent, and this way is basically the assignment of priority to the interrupts. So that is why priority priority assignment is important in interrupts, and it is not important in normal procedure calls. Why do IO devices place the interrupt vector on the bus? So the main reason this interrupt vector is needed is for identification of the device that is interrupting the CPU. So recall, in our systems we have, let's say, one CPU and there is an interrupt line. Let's say this is the interrupt line of the CPU. Several IO devices are attached to this one interrupt line. Let's say you have a hard disk here, you may have some optical drive here, or you may have some other IO devices, keyboards and so forth, right? There are so many IO devices and number of IO devices that are connected to the same interrupt line of the CPU. So all of these, any of these IO device, whenever it needs to send an interrupt to the CPU, it will have to assert a signal on this interrupt line. Now the problem is, the CPU receives the interrupt, but then CPU, how does the CPU know which of these devices has caused the interrupt, whether it is the hard disk or is it a keyboard or is it some other IO device? So the way these IO devices identify themselves is with the help of this interrupt vector. So as we discussed in the class, once the interrupt has been acknowledged, the interrupting IO device will place a small integer on the bus, which will help the CPU recognize or identify the device. So this question is about computing mean access time for the hard disk, assuming there is a disk cache. So recall, in the class we discussed that sometimes a portion of the main memory, let's say this is our RAM, is reserved, and let's say this is our hard disk. A portion of this RAM is reserved as a cache to the hard disk. So for example, let's say this bottom portion of the RAM is reserved as a cache for the hard disk. So the way this works is, the recently accessed blocks from the hard disk would be saved here. Now whenever CPU wants to get some data, it will first check this RAM cache. If the data is found here, it will be returned from here. There is no need for the CPU to go read the hard disk. However, if there is a miss in this cache, and then so if there is a miss, then only then the CPU can needs to go and read or access the hard disk. Okay, so this question is saying that, let's assume if the data that CPU is looking for is found in this cache, in the disk cache, then it takes 1 millisecond. However, if the data is not found and you have to access the hard disk, then accessing the hard disk alone takes 100 milliseconds. Okay, assuming that the hit rate in this cache, this is 25%, what is the mean disk access time? So the fundamentals of finding the mean access time remain exactly the same as for the RAM cache. So for basically the mean access time is given by, so let's basically we have to compute the weighted average, right? So if the data is found in the RAM, then how much time it takes? It takes 1 millisecond, right? What is the hit rate? 25%, right? So the probability that the data will be found in the RAM cache is basically 0.25. If the data is not found in the RAM cache, then you have to go access the hard disk. And the question says that assume all accesses to the disk first go to the cache, right? So what that means is, you'll first check the this RAM, it will take 1 millisecond, and then you will recognize that the data is not in the RAM, so then you will go access the hard disk, which will take additional 100 milliseconds, right? And the probability there would be a miss, the probability that you'll have to do this is basically 100 minus 25, 75%, right, which is basically 0.75. So this equation gives the weighted average of accessing the disk, right? So this is, if you solve this, will basically come to 76 milliseconds. All right, so in this question we are given two caches, cache A and cache B. Cache A is a direct map cache, cache B is an 8-way set associative cache. The question is asking us, the first part is asking us basically how much data can cache A, which is basically this direct map cache, hold. So let's find out the capacity. So we are given the address division of this cache, we are given the number of bits in the tag, the set index and the block offset field, and from here we have to figure out the size of the cache. So recall, first of all, this address is the memory address. This is the entire memory address. In a direct map cache had three fields, right? So it had block offset, set index and the tag field. So in the block offset we had log 2 base 2 of block size, which is also known as the line size, these many number of bits. The set index had log 2 base 2 of number of cache lines, right, these many bits, and all the remaining bits, these go to the tag field, right? So how do you find the size? So that so cache size is basically the line size, the size of each line multiplied by the number of lines. Okay, so the line size, as you would guess, can be derived from this block offset, right? So the block offset is log 2 base 2 of the block size. The block size is basically the line size, right? So if the block offset, as the question says, has 8 bits, this has 8 bits, so what would be the size of the block? So the block size of the line size would be 2 to the power 8. Okay, and number of lines, this we can derive from the set index. So the set index is basically log 2 base 2 of number of cache lines, right? So if the set index, as the question says, has 7 bits, so how many lines should there be in the cache? That would be 2 to the power 7 lines. Okay, so the cache size would be simply 2 to the power 8 multiplied by 2 to the power 7, which is basically 2 to the power 15 bytes, which is, so we have to convert this into metric prefix. So this would be 2 to the power 5 multiplied by 2 to the power 10, which is, so 2 to the power 5 is 32 and 2 to the power 10 is a kilo, right? So this is 32 kilobyte. That's the size of this cache. The answer to that question is also given here, right? So it's 32 kilobyte. The next question is, how much data can cache B hold? All right, so let's solve that over here. So cache B is an 8-way set associative cache. So once again recall that the address division of a set associative cache has three parts. Once again, it has the block offset, the set index and the tag field, right? So the block offset is again log 2 base 2 of block size, set index is log 2 base 2 of number of sets, right? Not number of lines, number of sets, and all the remaining bits are your tag bits, right? So the question says that so the question here says as there are 7 bits in the block offset, there is 5 bits in the set index, and then the tag has 20 bits. Okay, so basically the cache size here in this case would be set size multiplied by number of sets. Okay, so how do you find the set size? So set size is basically line size or block size multiplied by number of lines per set, so number of lines in each set. Okay, so the line size is basically the same as the block size, right? So if the block has 7 bits, the line size should be 2 to the power 7 bytes. Okay, that's straightforward. And notice that we can do this because both this so this cache B, this is a, notice this is a byte addressable memory. Also the direct map cache that we worked on in the previous example, that is also byte addressable memory, and that's why we can directly compute the line size from the block size. The computation will change a little bit if this was a word addressable memory, so we'll come to that later. All right, so the line size is 2 to the power 7, and the number of lines per set, notice that this is an 8-way set associative cache, right? So this 8-way means every set has 8 lines, right? So 8 is 2 cube, right? So basically your set size then becomes, so your set size is 2 to the power 7 into 2 cube, which is basically 2 to the power 10 bytes. So this is your set size, 2 to the power 10 bytes. Now just let's find, substitute this value here in the cache size. So the cache size is set size into number of sets. So we also need to find out the number of sets before we can do the substitution. So notice that the set index is log to base 2 of number of sets, right? So if there are 5 bits in the set index, the number of sets would be 2 to the power 5. Okay, so from here basically the cache size is equal to, so the set size, which is basically 2 to the power 10 here, so set size is 2 to the power 10 multiplied by the number of sets, which is 2 to the power 5. So this is basically 2 to the power 5 is 32 and 2 to the power 10 is a kilo, right? So this is 32 kilobytes once again. The solution to the same problem is also given over here. Alright, so this question over here is asking us for the same two caches that we saw in the previous two questions. Which of these two caches, A and B, the direct map cache and this 8-way set associative cache, which of these two is likely to have a higher hit rate and why? So recall from our discussion in the class that in a direct map cache, even when your cache is not full, multiple popular addresses could be competing for the same cache line, right? And therefore you may have evictions in the cache even when the cache is not completely occupied. As opposed to this, in an 8-way set associative cache or in an n-way set associative cache, every address maps onto a set of lines, right? So a set in this case has 8 lines. So even if there are multiple popular addresses that are mapping onto the same set, they can be accommodated within these one of these 8 lines, right? So it is likely, it is so most likely this direct map cache will have a much higher miss rate as compared to the set associative cache. So in other words, this set associative cache would see a higher hit rate. So the next question here is, which of these two caches, the direct map cache and the 8-way set associative cache, is likely to have a shorter access time, or in other words a faster access time? So recall that the direct map caches always have the fastest access time, and that's mainly because in direct map cache you only have to check one tag. The memory address maps onto a single unique cache line, so you just check the tag of that line. It's either a hit or a miss, no need to check any other tags. As opposed to this, here in this 8-way set associative cache, the memory address will map onto a set of 8 lines, so you will have to check up to 8 tags before you determine whether it's a hit or a miss. So the faster access goes to the direct map caches. The solution is also summarized over here. Now this question is also similar to the previous caching question. Here again we are given two caches, A and B, the direct map cache and the set associative cache, but the main difference here is these are now word addressable caches, right? This is not byte addressable. So let's see how this size computation changes if you have word addressable caches. So here the first part is asking us to compute the size of cache A, right? So once again, as we have seen, the address division would be in three parts: block offset, set index and tag. For this direct map cache, block offset is log to base 2 of block size, and set index is basically log to base 2 of number of cache lines. Okay, and all the remaining bits are basically in your tag field. So the question says that this block offset has basically 8 bits. So what that means is every block will have 2 to the power 8 words, right? So each block has each block has basically 2 to the power 8 words. So the size of each block would be the number of words. So the block size is basically number of words in your block multiplied by word size. Okay, so basically in this case the number of words is 2 to the power 8 and word size is 2 bytes, right? So this multiplied by 2, which is 2 to the power 9 bytes. This is your block size. okay, 2 to the power 9 bytes. Now the cache size remains the same, right? So I mean the formula for the cache size is basically block size multiplied by number of blocks or number of lines in your cache. Okay, so block size is 2 to the power 9 as we computed, and the number of lines is computed from the set index, right? So set index is log to base 2 of number of cache lines. So if set index, the question says, has 7 bits, so that means the number of lines in the cache would be 2 to the power 7. Okay, so from here we get cache size, we just substitute these, so we get 2 to the power 9 is our block size multiplied by 2 to the power 7, which is the number of lines or blocks in the cache. So this is basically 2 to the power 16 bytes. So this is, let's convert this into metric prefix. So we get 2 to the power 6 into 2 to the power 10 bytes. 2 to the power 6 is 64 and 2 to the power 10 is a kilo, right? So we have the size is 64 kilobytes. The next part of this question is now asking us to compute the size of this cache B, which is a set associative cache. Everything else remains the same pretty much as in the previous problems. The main difference is this, again, this is a word addressable memory. So once again, let's remind ourselves the address division. So this is our memory address divided into a block offset, a set index, and a tag field. So block offset once again is log to base 2 of block size. Set index is log to base 2 of number of sets, right? Not lines, because this is a n-way set associative cache. So once again, cache size is basically set size multiplied by number of sets in the cache. Okay, so set size, as we have seen, is basically block size. So block size or line size multiplied by number of lines or number of blocks per set. Okay, so first of all we have to figure out the block size. Now recall that the block size is derived from the block offset. So the block offset in this case has 7 bits, which basically means this is the block size will have, so block size is basically 2 to the power 7 words, right? So which is basically 2 to the power 7 multiplied by the word size, right? Word size is 2 bytes, so 2 to the power 7 into 2 bytes, so this is basically 2 to the power 8 bytes. That is the, so that's the block size. And number of lines per set, this is derived from this, so it is already given this is an 8-way set associative cache, right? So the number of lines per set is 8, which is 2 cube. Okay, so from here we get so from here basically the set size is given by the block size, which is 2 to the power 8 bytes multiplied by the number of lines per set, which is 2 cube. So this is basically 2 to the power 11 bytes. This is our set size. Now from here we can, so using this we can derive this cache size, right? So first of all, what is the number of sets in the cache? So recall that number of sets is determined by this set index, right? So set index is log to base 2 of number of sets. It is given that set index is 5 bits. So what that means is number of sets is 2 to the power 5 in this case. Okay, so now just substituting these values, cache size is given by set size, which is 2 to the power 11 bytes multiplied by number of sets, which is 2 to the power 5. So this is basically 2 to the power 16 bytes. Converting this into metric prefix, we get 2 to the power 6 multiplied by 2 to the power 10 bytes, which is basically 2 to the power 6 is 64 and 2 to the power 10 is a kilo, so this is 64 kilobyte once again. So that's the size of our 8-way set associative cache. The solution is also given over here, so actually it's unfortunately overlapping, but it is the same answer, 64 kilobyte. The solution is also summarized over here in this slide, and it's the same answer, 64 kilobyte. A performance optimization is applied to the branch detection unit, which makes it twice as fast. So the branch detection unit is used 25% of the time. What is the overall speed up of the system? So notice that this is a typical question on Amdahl's law. So first of all, you should remember the Amdahl's law. The overall speed up is given by So the overall speed up is given by s divided by p plus s into 1 minus p, right? So where s is basically the amount of speed up that you can get from the optimization, p is basically the portion of the program or portion of the system that you can optimize, right? So in this case here, let's quickly figure out these values. So here the s, the speed up is, the question says, is twice, so it's twice as fast, so s is equal to 2. And the portion of the program, this optimization is applied to the branch detection unit, which is used only 25% of the time, right? So this fraction that is sped up is 1 by 4. Okay, so let's just substitute these values in this equation and figure out the final answer. So the overall speed up basically becomes 2 divided by 1 by 4 plus 2 into 1 minus 1 by 4, right? So this is basically so let's just do this here, right? So this becomes 2 divided by 1 by 4 plus 2 multiplied by 3 by 4. This is 2 divided by 1 by 4 plus 6 by 4, which is basically, this becomes, so if you take this up, it becomes 4 into 2 divided by 7. This is 8 by 7, right? This is the overall speed up that you can get. So the answer is also summarized over here. So the next question over here is asking us to fill out the time chart for the execution of these instructions on a pipelined ANA architecture. So let's start with the first instruction here. Recall that the 5 stages in the pipeline are instruction fetch, decode, execute, memory access, and write back. So the first instruction cannot have any dependencies, so it will smoothly sail through the pipeline. So it goes through instruction fetch, decode, execute, memory access, and write back. The OR instruction, let's see whether there is any dependency. So fortunately, you see the AND writes into R1 and OR does not read R1, so there is no dependency. So OR basically fetches here as soon as the fetch is free of the AND, and then it will decode, execute, memory access, and write back. Next we have the load word instruction. The load word would read R1, and OR is not writing into R1 but AND is writing into R1, so there is a dependency between the AND and the load word. Okay, so let's see how this works out. So the load word will fetch here as soon as the fetch is free, then it will move on to decode. Now can it move on to with the execute? So the problem is, you see at this point now, so for this question we are assuming that there is no branch prediction and there is no data forwarding available, right? So basically what that means is this load word needs to wait for the write back, this write back of AND to finish, right? So we'll have to hold it here in the decode for one more cycle, and then it can move on to execute, memory access, write back. Let's come to the LUI. So LUI, recall, it loads the higher order 8 bits of this register R2 with this immediate 8, right? So LUI both reads R2 as well as writes into R2. So is there any dependency? Notice that load word is writing into R2, right? So there is a dependency between LUI and this load word. So this LUI would fetch here, and it cannot move on to decode because decode is busy, so it will decode here. Now at this point load word is not yet finished writing, so basically LUI has to wait until the write back of load word, so it will be in decode until this point, and then it can move on to execute, memory access, and write back. Be easy R0 R0. So obviously there is no, be easy only reads R0, and there is no dependency between be easy and the previous two instructions because nobody writes into R0. Also the content of R0 cannot change, so R0 will fetch here. Now the decode is busy, so it will be kept in the fetch until cycle 8, and then after this it can move on to instruction decode, execute, memory access, and write back. Okay, now recall the instruction that follows the be easy, it faces a control hazard. The problem is, until this be easy is resolved, we don't know whether the next instruction to be executed will be AND or it would be the target instruction. Now in this case, notice that because we have be easy R00, even if the branch is taken, we will anyways execute the AND instruction. So this is just an illustrative example, but nevertheless we will have a control hazard at this point. So the AND will fetch here. This is where the first time fetch becomes free of be easy. Then it will basically, then it cannot move on to decode because it has to stay. Recall that in order to resolve the control hazard, we hold the following instruction, the instruction that follows the branch instruction, into the fetch until the memory access stage of the branch is over, and then it can move on to decode, execute, memory access, and write back. Okay, now after this we have the not instruction. The not instruction basically reads it reads R5, and the R5 is not written by, so AND does not write into R5, BEZ does not write into R5, so there is no problem, there is no dependency over here. So not fetches here in cycle 12, and then it moves on to decode, execute, memory access, and write back. This add it reads R3, and not is writing into R3, right? So there is a dependency between this add and not. So basically this add will fetch over here, moves on to decode, but then it has to wait for write back of that not to finish. So it will be held in the decode until this cycle 16, and then it can move on to execute, memory access, and write back. Finally we have the store word instruction. So the store word instruction basically reads R3 and R7, right? So notice that add writes into R3, not writes into R3, right? So there is a dependency between this store word and this add and also there is this dependency between the store word and the not, right? So let's see how this goes. So this will fetch here in cycle 14, then it cannot move into decode yet because the decode is busy, so it remains in fetch until cycle 16, then it moves on to decode. But the problem is, you see, at this point the write back of not has already passed, so that is not a problem. However, we still have to wait for the write back of the add to finish. So this is going to be held in the decode unit until cycle 19, and then it can move on to execute, memory access, and write back. The solution for the problem is also given over here. Alright, so the next question is the same set of instructions, and we again have to fill out the time chart for this. However, in this case we can assume that both the branch prediction as well as data forwarding are available. So let's see how that changes the flow of instructions here. So there is no problem with the first instruction because there cannot be any dependency, so it will fetch, decode, execute, memory access, and write back. The OR instruction, we have seen there is no dependency between OR and AND, so OR reads R4 and R7 and does not write in either of them, so it will fetch here, then decode, execute, memory access, and write back. The load word reads R1 and the AND writes R1, right? So there is a dependency between the load word and AND. So the load word will basically fetch here, move on to decode. Now you see we will ideally need to wait until the write back of AND. However, because there is data forwarding available and the final result that needs to be written in R1, that would be available here at the end of the execution of AND. So that can be forwarded from here to the execute stage of the load word, and therefore the load word doesn't need to wait, it can simply move on to execute, memory access, and write back. Okay, next we have LUI. So LUI basically reads R2 and also writes into R2, and the load word is writing into R2, right? So there is a dependency between this load word and the LUI instruction. So the LUI will fetch here, decode here, but the notice that it cannot move on to execute because you see the data that this LUI needs in R2 would be available in load word at the end of its memory access cycle. Okay, so it cannot be forwarded into the execute stage of LUI yet. So that's why the LUI will need to be held in the decode at this point, and then you don't have to wait for the write back of load word to finish, because if now it moves on to the execute, from here the data can be forwarded to the execute stage of LUI. So there is only one cycle stalled, and then from here it can move on to memory access and write back. Next we have this BEZ instruction. Again, there is no dependency between BEZ and the previous two instructions, so it can simply fetch here, it remains in fetch because the decode is busy, then decodes, execute, memory access, and write back. Following BEZ we have the AND instruction. Now let's assume that the AND instruction, we have a branch predictor as the question says, and we are assuming that it is 100% accurate. So let's assume that the branch predictor correctly predicts that this AND would be fetched and executed. So basically in this case we don't need to hold the AND in the fetch until the branch is resolved. this AND will be fetched here, and then it will simply continue executing through decode, execution, memory access, and write back. Okay, because we have 100% accurate branch predictor. And notice that there is no dependency between the AND and any of the previous two instructions, right? So the AND reads R7 and R3, and these are not the destinations in any of the previous two instructions. So moving on to the next instruction, we have not basically reads it reads R5, and R5 is not a destination in any of the previous two instructions, so there is no dependency here. So it will simply fetch here, decode here, execute, memory access, and write back. The add I instruction reads R3 and not instruction writes into R3, so there is a dependency between not and the add I instruction. Okay, so this add I will fetch here, it will decode here. Now notice that because we have this data forwarding, we don't need to hold this add I into the decode. The data that we are looking for, that will be available at the end of the execute stage of not. So from here, if this add I moves on to execute here, the data can be forwarded to its execute stage, right? So there is no need of stall. Then it moves on to memory access and write back. Oops. Finally, we have the store word. The store word reads R7 and R3, and you notice that this R3 is a destination in the add I, so there is a dependency between add I and store word. It is also destination in not. So the store word will basically fetch here, decode here. Now do we need to wait until the write back of this add I? So fortunately, notice that the execute for the not is already passed, and also the execution for add I is here. So basically the data that we're looking for in the execute stage uh, of store word. So actually we don't need the value of R3 in the execute stage of the store word. Notice that this R3 would be needed in the memory access stage when we want to write into the memory, right? So and the data would actually be available at the end of the execute stage of add I. So from here it can easily be forwarded, so there is no need for waiting, so it can simply move on to execute, memory access, and write back. Okay, so the data can easily be forwarded from here to the memory access stage of the store word. So this is our solution. The solution to the same problem is also summarized here on this slide. So this question is about finding the average memory access time in a cache system. So notice that the question tells us the cache access time is 10 nanoseconds, the main memory access time is 300 nanoseconds, and the cache hit rate is 80%. Right, so recall that this is once again a weighted average problem. So what if the, and also notice that we are assuming that all memory references first go to the cache, right? So whether it's a hit or a miss, it will first check the cache. All right, so assuming that the memory access is returned from the cache, right? So that will take 10 nanoseconds, right? If it is found in the cache. So what is the probability of this happening? The hit rate is 80%, right? So 0.8 is the probability of a hit in the cache. Okay, if the reference is not found in the cache, then we have to go to the main memory. Now how much time will that take? So notice that you first check the cache, which will take 10 nanoseconds, and then you'll find it was a miss, and after that it will take 300 nanoseconds additional time to get the data from the main memory, right? And the probability of this happening is 1 minus 0.8, which is 0.2. Okay, so this is our average memory access time with this cache. Now if you do the math here, you'll find this comes to 70 nanoseconds. This problem is about the address breakdown for a given cache system. So we are given a four-way set associative cache. The block size is 16 bytes and the addresses are 32 bits. The total cache size is 8 kilobyte, right? So let's recall that with the set associative cache, the address breakdown looks like this. So if this is our memory address, we have it will break down into a block offset, a set index, and a tag field, right? And the block offset has log2 base 2 of block size, number of bits. The set index will have log2 base 2 of number of sets, because this is a set associative cache, and all the remaining bits will go to the tag field, right? So the block of the block offset should be straightforward here. It's a byte addressable memory, and the block size is 16 bytes, right? So the block offset is simply log 2 base 2 of 16, which is 4 bits. Okay, so this is 4 bits. Next we have to find the set index. So the set index is basically log 2 base 2 of number of sets. Now notice that the number of sets is not directly mentioned here, so we'll have to compute that. So recall, number of sets is basically the cache size divided by the set size. Okay, so how do you find the set size? So basically set size is given by line size or block size, the size of each line, multiplied by the number of lines in each set. Okay, so the block size is the same as the line size. So block size is 16 bytes, so the line size is also 16 bytes, and the number of lines per set, this is a 4-way set associative cache, right? So the number of lines per set would be 4. So this is basically 16 is 2 to the power 4 and 4 is 2 square, right? This is 2 to the power 6 sets. I'm sorry, 2 to the power 6 bytes in each set. So this is the set size. So now we can use this value to compute the number of sets, right? So we have cache size is given as 8 kilobyte. So 8 is 2 cube and a kilo is 2 to the power 10. So the cache size is 2 to the power 3 into 2 to the power 10, and the set size is 2 to the power 6. So divided by 2 to the power 6, this is basically 2 to the power 13 divided by 2 to the power 6, which is basically 2 to the power 7 sets. Okay, so essentially the set index will have log 2 base 2 of this 2 to the power 7, which is basically 7 bits. Okay, so the set index in this case, this field here, this has 7 bits. All right, and all the remaining bits go to the tag field, right? So the tag field in this case, the total address is 32 bits, so the tag will have 32 minus 4 bits of block offset minus 7 bits of set index, right? So this is basically 32 minus 11, which is basically 21 bits. So this is your tag field. The solution to the same problem is also summarized over here. So notice that we have 4 bits for the block offset, 7 bits for the set index, and 21 bits for the tag field. So this question over here is asking us to find out all possible data dependencies in this code, right? So let's start from the first instruction. The first instruction cannot be dependent on anything because there is nothing before it. For all other instructions, recall that we just have to look at what are the sources for that instruction. So for example, if you look at the subtract instruction, the subtract instruction reads R3 and R2. Now we should simply check whether R3 and R2 are destinations in any of the previous two instructions, right? So you see R3 is a destination here in the add. So there is clearly a dependency between the add and the subtract, right? So our first dependency is basically between instructions 1, 2 due to register R3, right? R2 is there is no conflict because of R2. Moving on to instruction 3 over here. So load word will read R5, and we just need to check R7 is the destination for load word, so we don't need to worry about R7. So R5 we need to see whether R5 is a destination in any of the previous two instructions, right? So R5 is a destination in the subtract, and there's no other problem with the add instruction. So there is a dependency between the subtract and the load word. So the second dependency we found is basically between instruction 2 and instruction 3 due to R5, right? This register. And finally we have this add instruction. So add reads R7 and R2. We just check whether R7 and R2 are destinations in any of the previous two instructions. So notice that R7 is a destination in the load word. There's no problem with the R2. So there is the third dependency that we find is between instructions 3, 4 due to R7. So these are our 3 dependencies. The answers are also summarized over here. So the next question here is, how many data dependencies exist in this code? Alright, so this question over here is asking us which of the dependencies in this code that we found on the previous slide can be resolved by using data forwarding, right? So recall that if there is any dependency on an arithmetic or logic instruction, that can be resolved using data forwarding, right? So this first dependency that we found between these instructions 1 and 2, right, because of R3, this can be resolved because subtract depends on add, and add is a arithmetic and logic instruction, so this can be resolved by data forwarding. Similarly, this dependency between 2 and 3 instructions 2 and 3, which was because of R5, once again you see this load word depends on us on subtract, so subtract is a arithmetic instruction, so this can also be resolved using data forwarding. The next question here is which dependencies will cause a stall, right? So notice that the last dependency between this instruction 3 and 4, right, you see this add depends on the load word because of R7. Now the problem, so whenever there is a instruction depending on a load word, result of the load word, we cannot eliminate all the stalls because the load word happens in the memory access stage, right? So recall that. So let's quickly draw the pipeline here, right? So this load word will fetch, then decode, execute, memory access, and write back, right? This add will fetch, decode, and notice that if we allow it to execute here, the problem is the data that we want to write into R7, that would be available at the end of the memory access of the load word, right? So there is no way we can forward this data to the beginning of the execute stage here, right? So therefore the execute cannot happen here. We must hold this add for one more cycle in the decode, and then we can forward it to the execute stage, right? So there would still be a one cycle stall in spite of data forwarding. So the third dependency that we had between the load word and the add instruction, that will cause a stall. The answers are also summarized over here. So here is another question about the speed up. And now the question says that you have a computing system that consists of 60% of CPU activity and 40% of hard disk activity. The customers are complaining that the system is slow, and therefore you do some research and you discover that you can upgrade your disks and make them 2.5 times faster. So this is the speed up you can get on the disk, and you can also upgrade the CPU and make it 1.4 times faster. Okay, now the question is what would be the total speed up if you could implement both the upgrades? Notice that the question is not saying just one of them, choose one of them. So this is asking what if you had time and money to do both the upgrades, how much speed up can you get? Now assume that both the CPU and the disk operations take same number of clock cycles, say n, right? So you can approach this problem using Amdahl's law, but in this case there is another simpler way you can do it without using the Amdahl's law. You only basically use the fundamental fact that the overall speed up is always given by the original time divided by new time. Okay, so if assuming that you have to, let's assume you need to execute total of 100 instructions, right? So to execute 100 instructions on the original machine, if each instruction is taking n cycles, right? So the original time, so basically t original would be for 100 instructions would be simply 100 multiplied by n, right? Because each instruction takes time n times, and each instruction is either CPU or disk instruction. So this is the original time. Now let's see what we can do to this time if we were to employ our optimization, right? So let's say we have these 100 instructions. Out of this, the question says 60% is CPU, so these 60% instructions, so let's say these are CPU instructions, 60 instructions, and 40 instructions are your hard disk instructions. The question says that we can upgrade the disk to make it 2.5 times faster, right? So if originally the 60 instructions were taking, so 60 instructions originally will take 60 n time, 40 instructions originally will take 40 times n time. Now if you can upgrade the CPU, I'm sorry, if you can upgrade the hard disk 2.5 times, then this time will become, the new time will become 40n divided by 2.5, because you have sped up the hard disk by a factor of 2.5. Similarly, if you can speed up the CPU by a factor of 1.4, this 60n will reduce to 60n divided by 1.4. okay, so the new time that you get, t new, will become basically 60n divided by 1.4 plus 40n divided by 2.5. so if you do the math, you'll find this comes to 58.86n. okay, So your overall speed up, let's just plug in this is your new time and we have the original time 100n. So our overall speed up basically becomes, so original time which is 100n divided by new time which is 58.86n, right? So this is basically roughly equal to 1.7. So this is going to be a speed up of a factor of 1.7. The same solution is also summarized over here. So this question is about Amdahl's law for parallel computers. So recall from our discussion in the class that the Amdahl's law for parallel computers is overall speed up is equal to basically n divided by p plus n into 1 minus p, right? So if you have n processors and let's say a fraction p of your program is fully parallelizable, that can make use of all the n processors, then still the overall speed up you can get is basically limited by this expression. So the question is asking compute as a function of p the maximum possible speed up even if you have, let's say, infinite CPUs, right? So if you want to compute how much maximum speed up you will get for over infinite CPUs for a given process that has a portion p parallelizable, right? So that would be basically you simply compute limit n tends to infinity for this function n divided by p plus n into 1 minus p, right? So let's do some simplification. So let's divide the numerator and denominator by n, right? So divide this by n, divide this by n, divide this by n, so you get, so this n by n becomes 1, and here p by you remain with p by n plus this n and this n cancels out, you have 1 minus p, right? So here if you substitute limit n tends to infinity, right? So basically if n tends to infinity, this term will tend to 0, right? And everything else will remain the same, right? So basically this limit would be simply 1 divided by 1 minus p. This is the maximum speed up you can get even if you have infinite number of CPUs. So what does this mean? Let's assume that 90% of your program was parallelizable, right? So if this p was equal to, if p was equal to 0.9 or 90%, the maximum speed up that you can get would be 1 divided by 1 minus 0.9, which is basically 1 divided by 0.1, which is basically 10. So even if you have infinite CPUs, if 90% of your program is parallelizable, you can still get only a factor of 10 speed up. So the same answer is summarized over here as well. So recall in the class we talked about 4 different types of parallel performance optimization techniques, right? So the first one was optimizing for the common case. Then we had this increasing throughput by hiding latency. Then we talked about RRC, which is reducing response time via concurrency, and then ITC was increasing throughput via concurrency. So this question is asking us which for these given popular parallel optimization techniques, the caching, coprocessor, and so forth, which of these 4 classes they belong to. So basically which of these 4 optimizations are these employing? So let's start with caching. So recall that caching, uh, so caches are intended to store the most commonly and most frequently accessed data, right? So the data that is most likely to be used by the CPU, that we will store in the fast caches so that the CPU can get to those data items quicker and it doesn't have to access them from the slower main memory, right? So essentially the caching is increasing or optimizing the access speed for the most common accesses, right? So caching is an example of optimizing for the common case. Now, so next we have the coprocessor, right? So recall the way we talked about this was if there is a certain operation that is very popular and very frequent in your system, right? So what we can do is we, instead of having main processor handle that popular or frequent request, we can develop a specialized and more optimized processor to take care of those kinds of requests. So for example, if network packets, let's say processing network packets is a very frequent operation in our system, then we can develop a network processor which is optimized and specialized in processing network packets. So this common request can then be, whenever this common request is received by the main CPU, it can be delegated to this coprocessor and the main CPU can do something else in parallel, right? So because these coprocessors are typically optimized for delegating some significant chunk of common or frequently occurring requests. This is also an example primarily of optimizing for the common case. Next we have the parallelized programs. So let's take a quick example, right? Let's assume that we had a certain process which was taking, let's say, a total of 9 seconds, right? Now, so if this was a single threaded process, so it could run only on one CPU at a time, right? So on one CPU, if you execute this process, let's say P1, it will finish in 9 seconds. So 9 seconds is the response time, right? Now let's say you implement a multi-threaded version of this process. So now this process can be divided into 3 threads, T1, T2 and T3, each of which take 3 seconds each, right? And now because these are 3 threads, let's assume that they are perfectly independent. So the thread T1 can run on core 1, T2 can run on core 2, T3 can run on core 3, right, in parallel. So if you can do this, you can parallelize this program and run it simultaneously on 3 cores. It will finish, so C1 will finish in 3 seconds, C2 will finish in 3 seconds, and C3 will also finish in 3 seconds, right? So the response time that you will get for P1 for this multi-threaded version is now 3 seconds. So notice that your response time due to this parallelization has come down from 9 seconds to 3 seconds, right? So this is basically an example of reducing the response time via concurrency, RRC. Next we have the pipelining, right? So recall what pipelining was doing. So in our ANA pipelines, we talked about this 5-stage pipeline. So we have this instruction fetch, decode, execute and memory access and write back, right? So we saw that when we divide the execution of an instruction into these several stages, the total time it takes to finish one instruction, that doesn't go down. In fact, because this division between these stages is typically not clean, the overall time that it takes to finish an individual instruction may actually go up slightly. However, now that you have these 5 different pipeline stages, you may have multiple instructions being operated on different stages simultaneously in the pipeline, right? So you get a lot of parallelism. So because you are parallelly operating on several instructions simultaneously, up to 5 instructions simultaneously, you are able to hide this increased latency of individual instruction execution. Okay, so pipelining is basically a classic example of increasing throughput via hiding latency, ITHL. All right, now finally we have this replicated web server. So replicated web server is basically, assume that you have a web server. Let's say there is a very popular web server that serves some content, and there are millions of requests for that content, right? So obviously if one web server is let's say one web server is able to so you have one web server and it is able to service, let's say, 1,000 requests per second, right? And let's say the content is very popular, there are tens of thousands or let's say millions of requests per second. So to increase the number of requests that can be served per second, you can replicate this content, right? So the same content can be copied on another web server, let's say, that can also service 10, let's say 1,000 requests per second, right? And so on, right? We can go on replicating until we are satisfied with the amount of requests that we can serve per second. So essentially here what we are doing is we are increasing the throughput of this website or this web server by replication. Okay, so each request is still taking the same time, but just that we have a greater number of hardware, greater number of web servers, so they are now able to serve much greater number of requests per unit time. So we have increased the throughput by employing this concurrency, right? So this is an example of ITC, right? This last one, increasing throughput by concurrency. So these answers are also summarized over here on this slide. So we are given a fully associative cache that has only 4 cache lines. It uses LRU replacement policy. The memory addresses are 20 bits size, and it's a byte addressable memory. The block size is 256 bytes. What that means is every cache line can store 256 bytes. The question is how many bits are there in the block offset. So this is pretty straightforward. Recall that block offset, number of bits in block offset, is basically log2 base 2 of block size, right? So in this case we know that the block size is 256 bytes, so basically 256 is 2 to the power 8. So this implies basically block offset will have log2 base 2 of 2 to the power 8, which is basically 8 bits. So the answer is also over here. So in the follow-up question over here, we are still given the same cache as on the previous slide, and what we have to do is, for these sequence of address accesses that is shown in the table over here, we have to figure out whether it results in a hit or a miss if we are using this cache described here, right? So this cache has 4 lines. Each line is 256 bytes, and it is a fully associative cache, right? So recall that if you have a fully associative cache, the memory address is going to be divided into 2 parts, right? You will have a block offset and a tag field. Okay, so the block offset is log2 base 2 of block size, right? So and the remaining bits would be your tag field. So in this case, the question says addresses are 20 bits, right? So and 256 byte is a block size, so the block offset will have log2 base 2 of 2 to the power 8, which is 8 bits, right? Because 2 to the power 8 is 256, and the remaining bits in the tag field would be 20 minus 8, which is 12 bits. Okay, so this is first thing we should realize in solving this problem, the address division. So why is this useful? Recall, so let's start from here, right? Let's start from the top, right? So the first address, the let's say this is your cache. Let's assume that there are, so the question said there are 4 lines, so the cache starts out empty, right? Now, so the first address is obviously going to be a miss. It cannot be hit, the cache was empty. So now the question is, in response to this miss, what addresses do you bring in, right? So we first have to break down this address into the tag and the block offset field, and then so basically the address is in hexadecimal, so this is hexadecimal 1 2 3 4 5, right? So each bit here, each digit basically represents a 4 bit, right? So this is 4 bits, this is 4 bits, this is 4 bits, and so forth, right? Every digit here is 4 bits. So the question is, so basically from the question we know that 8 bits is block offset, right? So basically these last 2 bits, this is your block offset, and this first 3 bits, this is your tag field. This is 12 bits, and this last 2 bits, this last 2 digits is 8 bits, right? So the tag is hexadecimal 1 2 3. Recall from our discussion, in a fully associative cache, whenever there is a miss, we will bring in everything that has this common tag, right? So basically the common tag hexadecimal 1 2 3 will belong to all the addresses in the range hexadecimal 1 2 3 0 0 to hexadecimal 1 2 3 FF. Okay, so this is the key to solving the problem. You need to first figure out the address division, and then you have to figure out, for every address miss, every cache miss, what range of addresses are brought in. Okay, so let's solve this problem here on the next slide. So this first access was a miss. Now let's say this is our cache over here, so let's create a cache, and it has 4 lines as given in the question. Each line is initially empty. Now in response to this miss, we have seen that this hexadecimal 1 2 3 4 5, this is your block offset, this is your tag. So in response to this miss, we'll bring in everything in the range hexadecimal 1 2 3 0 0 to hexadecimal 1 2 3 FF. Okay, uh, so that let's assume that all of that goes into the top line over here, right? So here we'll have hexadecimal 1 2 3 0 0 to hexadecimal 1 2 3 FF. So notice that the reason we are getting everything from 0 0 to FF is this least. So if you have this hexadecimal 1 2 3, and let's say we expand this least significant 8 bits, so everything that will have this common tag will be basically 0 0 0 0 0 0 0 0, right? It starts from here and goes all the way to 1 1 1 1 1 1 1 1, right? So this is basically in hexadecimal, this is hexadecimal 0 0, and this is hexadecimal FF. That's why we load this range of addresses. Okay, now just now we brought in this address range in the first line. So let's say, so here we have to keep the LRU information, right? Now because there are multiple lines, we cannot just keep 1 bit of LRU information. So let's say we mark a 1 in front of a line anytime it is accessed, right? And a 0 in front of all other lines. So 1 indicates access, 0 indicates no access. Okay, so the first one was a miss. Now the next address is hexadecimal 12397. Now is this going to be a hit or a miss? We have 12397. Notice that hexadecimal 123, we just search for the tag in the cache, right? So hexadecimal 123, this tag is present in the cache. Notice this is hexadecimal 123 starting from this, so everything with this tag is already present in the cache, so this is going to be a hit. Similarly, the next address is hexadecimal 12346, right? Once again it has the same tag, so this is also going to be a hit. Next we have 23456, right? Now so hexadecimal 23456, now this tag 234, this is not present in the cache, right? The last two digits here, this is your block offset, so this is going to be a miss. Now also we forgot to maintain the LRU information, right? So for this next two accesses, these were also a hit on the first line, right? So we'll have two ones here and two zeros in front of the remaining rows. Okay, so the access information is important to maintain, as you'll see later on. So in response to this latest miss, hexadecimal 23456 will bring in everything in the range hexadecimal 23400 to 234 FF, right? Let's bring it in the second row over here, so we get everything hexadecimal 23400 to 234 FF here. We just now wrote in this row, so this we write a 1 here and 0 in front of all other rows. All right, so after this we have 23587. You see the tag is hexadecimal 235. Now this hexadecimal 235 tag is not present anywhere in the cache, so this is also going to be a miss. In response to this miss, in response to 23587, we bring in everything in the range 23500 to 235FF, right? So let's use this third row here, so we get hexadecimal 23500 to 235FF here. So we just now wrote in the third row, so we will mark a 1 here and a 0 in front of all other rows. Okay, next we have hexadecimal 12289. Now you see tag 122 is not present in the cache. We have 123, 234 and 235, so this is also going to be a miss. And in response to this miss, we'll bring in everything in the range 12200 to 122FF, right? Let's bring it in the last row here, the last cache line. So we have 12200 to hexadecimal 122FF. We just now access the last row, so we'll mark a 1 here and a 0 in front of all other rows. Okay, now after this we have hexadecimal 12357. So notice that 123 tag is present in the first line, so this will be a hit, and it hit in the first line, so this would be mark a 1 here and 0 in front of all of the lines. Okay, next we have hexadecimal 60000, right? So this tag 600, this is not present anywhere in the cache, right? So this is going to be a miss. Now the question is, in response to this, we know that we'll bring in everything in the range 60000 to 600FF, but the question is where, in which of these rows do we bring it in? So now we have to evict the cache, right? So we use LRU eviction. So let's find out which of these is the oldest cache line. Okay, so this line was accessed one cycle ago. This line, so this was accessed one cycle ago. This line was accessed 1 2 3 4 cycles ago. This line was accessed 3 cycles ago, right? And this line was accessed 2 cycles ago. So notice that this is our LRU line. Okay, so we'll evict this data in this line. So we'll evict this data over here and bring in the new data here. So we'll bring in hexadecimal 60000. So and we just now brought in data in the second line, so we'll mark a 1 here and a 0 in front of all other rows. Okay, next we have hexadecimal 12289. So this is again a hit, it hits in this last line. Notice that 122 is present, this tag is present in the cache, so this is going to be a hit. It hit in the last line, so we mark a 1 here and 0 in front of all of the lines. Next we have hexadecimal 23456. So the tag 234 is not present in the cache, right? We have 235 122 600 and 123, right? So this is going to be a miss. Now in response to this miss, again we have to evict something. So let's find out the LRU line, right? So the first line was accessed 3 cycles ago. This was the second line was accessed 2 cycles ago. The third line was accessed 1 2 3 4 5 cycles ago, and the last line was accessed just 1 cycle ago, right? So this is our LRU line. So we will now evict this line, the third line, and bring in the new data, hexadecimal 23400 to hexadecimal 234FF here. Now because we just now brought in the data in this third line, we mark a 1 here and a 0 in front of all other lines. Next we have hexadecimal 12399. So notice that the tag 123 is present here, so this is going to be a hit, and it hit in the first line, so we mark a 1 over there and a 0 in front of all other lines. Lastly we have hexadecimal 23587. Now 235 tag is not present right now, right? We have 123 600 234 and 122, right? So this is going to be a miss. And once again, in response to this, we'll bring in data in the range 23500 to 235FF, and we'll have to evict the LRU line from here. So I hope you get the idea of how to solve this problem. The solution to the same problem, the answers are also given over here. So this basically brings us to an end of this final review. I hope this was helpful. Obviously this is not a comprehensive review, it doesn't cover everything that could appear on the exam, so I highly encourage and recommend all of you to go through all the material in the lecture slides, solve again all the assignment questions, also revise this review slides, the review slides that you had from the for the midterm, and if you have the textbook, please complete the recommended readings. One last thing that I would like to mention is the best way, I keep saying this to many of my students, the best way to go through the review material is not just to watch this video or go through the slides once. You should basically try to solve all the questions yourself after going through this material once, right? And keep doing that until you can solve all the questions in one sitting, one go, without any assistance from the solutions. At that point you can be reasonably sure that you have understood or learned the material, and most likely it will come back to you when you need it during the exam. Okay, so good luck with the exams. Thank you very much, and let me know if you have any questions.